Let us continue with the different types of elements. So here that is used in finite element analysis. Next we will take up quadratic elements. The quadratic elements means the highest power of x or y in the displacement function is 2. For example, in that you have one-dimensional element as well as two-dimensional element. So in the case of one-dimensional element, example for one-dimensional element is bar element or truss element or beam element. So you will be having 3 nodes here like this. 3 nodes. So 1, 2, they are the end nodes, and the third node may be at the midpoint. So 3 nodes like this. So in the case of one-dimensional element, what happens? Only one coordinate will be there, that is x coordinate. Displacement model is defined as u of x is equal to a1 plus a2x plus a3 x square, where a1, a2, a3 they are the generalized coordinates. So here we can observe that the highest power of x is 2 here, that is n is equal to 2, highest degree, and m is equal to 3. M is the number of generalized coordinates 1, 2, 3, and highest power is 2, that is the value of n. So we will be having 3 nodes in the case of a one-dimensional quadratic element. So it's a combination, so one-dimensional quadratic element. Now we can go to the two-dimensional element. In the case of a two-dimensional element, normally CST element, that is constant straight triangular element. So you will be having 2 coordinates, both x and y coordinates will be there. The x will be like this and y will be like this. So there will be 2 displacement fields here. One is for the horizontal direction, another is for the vertical direction. In the horizontal direction we have the u, and in the vertical direction we have the v. So 2 displacements or 2 translations we can say. So both are functions of both x and y. So here both u and v are functions of x and y. So in this case the displacement model is defined as u of xy. There are 2 variables here, is equal to a1 constant plus a2 times x plus a3 into y plus a4 into x square plus a5 into xy plus a6 into y square. See the pattern how it has been written. So initial first term is always the constant term, then x term, then y term, then x square, xy and y square. You can see the symmetry here. So it is symmetrical about both x and y. That is very, very important. All the displacement functions, they will be symmetrical about both x and y. Or you can say it is cyclic order we have right. Similarly for v, in the vertical direction, the displacement function is given in the same manner. Only thing is this a1, a2, a3 coefficients of general coordinates, they are represented by b1, b2, b3 like that. So in this case you can observe the highest power here also it is 2 only. So y square, x square, it is 2 only, whereas that is n value is 2, whereas the number of generalized coordinates, if you take u or v, it will be 6, 1, 2, 3, 4, 5, 6, a1 to a6. So therefore m is equal to 6 here. So n represents the highest power of the variable, and m represents the number of generalized coordinates used to define the displacement function. Next type of element is cubic element. You see here cubic. Cubic means x cube term should come. Cubic element. In quadratic you have x square term highest. In cubic you have x cube term. Here you will be having 4 nodes. So number of nodes you can see it is equal to number of generalized coordinates. So that is very important. So number of nodes is equal to number of generalized coordinates, that is a1, a2, a3 like that. So that concept you have to remember. Okay. Generalized coordinates means a1, a2, etc. So these should be equal. So here there are 4 generalized coordinates a1, a2, a3, a4. So therefore the value of m is 4, and the highest power is 3. Therefore the value of n is 3. So there are 4 nodes here. So maybe if you take this length as L, so this can be L by 3, this can be L by 3, this can be L by 3. So you can take the nodes at equal distances from the ends. So this is for a bar element, one-dimensional bar element, that is cubic element. Now coming to two-dimensional in cubic element. See the concept here. So one-dimensional quadratic, two-dimensional quadratic, one-dimensional cubic, two-dimensional cubic. So when it comes to two-dimensional element, actually the minimum, the basic element is the CST element, constant strain triangular element. In that case, you can observe here we have 10 nodes. We have 10 nodes here. So each, you can see here, just like this line element, you have here for each line or edge of the triangle, you will be having 4 nodes. Similar to this 1, 2, 3, 4. Like that, for each you will be having 4 nodes, and at the center you will be having one node. Centroid. You can take it as centroid. You have one node 10. So here you have to, as I already told, displacement function always you have to write in the cyclic order with respect to x and y. So it should be symmetrical with respect to x and y. So how to write the displacement function here? Let us see. It is u of x is equal to a1 plus a2x plus a2 u of x comma y. This is not u of x. This is u of x comma y. V of x comma y. It's because it is two-dimensional. So two-dimensional means your u and v, they are functions of both x and y. That is the meaning. One-dimensional means it is only u. So u is a function of only x. That is the meaning of one dimension. Now here if you write on similar lines, just what we have done here, first term is constant term plus a2 into x plus a3 into y. So then you have to go to square term, x square term, then y square term, because it should be symmetrical. Then you have to go to x cube term, x cube, x square y, xy square and y cube. You can see here, initially we take x cube, then reduce the power by 1 and increase the power of y by 1. That means x cube is there, x square into y is there, then reduce the power of x by 1 means x, increase the power of y means y power 1 means y power 2. So that the total power always is 3, 2 plus 1 3, 1 plus 2 3, 3, 3. So the highest power is 3 here, therefore n is equal to 3. Then coming to m value is the number of generalized coordinates, which is 10 here. So there are 10 generalized coordinates, a1 to a9, a1 to a9 again, 6, 7, 8, 9, 10. So there are 10. So m is equal to 10 here. So there are 10 generalized coordinates, a1 to a10. Yeah, correct. M is equal to 10 here. So similar lines you can write for v of xy by replacing a1, a2, a3 by b1, b2, b3. So what you can say here is the number of generalized coordinates always depends on the number of nodes. So they are equal. Number of nodes is equal to number of generalized coordinates. So depending on the type of the element which we are choosing in the finite element analysis, so the corresponding displacement function we have to assume. So here all these generalized coordinates we have to find out using the boundary conditions, equilibrium conditions, compatibility conditions, etc. etc. Now to remember these things in a easy manner, a triangle has been developed called Pascal triangle, both for CST element as well as for quadratic element. Now let me explain. So very simple. So what we have to do here is to understand the Pascal triangle. First we will write 1 here, then x and y. So that is x to the power of 1, y to the power of 1, like that. Then next comes x square, x into y, y square. Please note that on one side x terms will be there, on another side other end y term will be there, and in the middle both xy terms will be there. Next row comes x cube. So what we have to do is increase the power of x by 1 here, and next term comes here, x cube means next is x square y. Horizontally when you move, you have to reduce the power of x and you have to increase the power of y. So x cube, x square y, xy square, y cube. Then comes x power 4 here, x cube, reduce the power of x by 1, x cube y, x square y square, then xy cube, then y power 4, like that it goes on. So this triangle is called as Pascal's triangle. Using this Pascal's triangle, once you know how to write the Pascal's triangle, you can easily write the displacement model. So for example, if you take only this one, so then u of xy will be only a1. So a1 refers to a single node, constant, straight, triangular, single node element. Then if you take the second row, so if you want to write the second row, we have to take the first row and second row both. So for the first row it is a1, for the second row it is a2x, a3y. So we have to add a1 plus a2x plus a3y. So this corresponds to 3 node CST element. So 3 node CST element. Next comes the third row. For writing the third row, we have to start from the first only. So this is a1 plus a2x plus a3y plus a4x square plus a5xy plus a6y square. See here. So this corresponds to 6 node CST element. So 6 nodes. There are 6 nodes. So I have taken 3 nodes at the vertices and 3 nodes at the midpoints. So later on we can derive the shape functions for all these elements. Next comes this fourth one. This one u of xy, that is the fourth row. So if at all you have to use this fourth row. So what happens for writing this fourth row? That is nothing but this element. So what is this element? So you will be having 10 nodes there. So that means 10 generalized coordinates will be there here. So you can see here, you have to start from here only, from the top. a1 plus a2x, you can see here, you can read out here. a2x plus a3y plus a4x square plus a5xy plus a6y square plus a7x cube plus a8xy plus a9xy square plus a10y cube. So you will be having 10 generalized coordinates and 10 nodes. So like this, you can write any number of general coordinates. If you give the next one will comprise of 1 plus 2 3, 3 plus 3 6, so 6 plus 4 10, 10 plus 5 15. So you will be having 15 elements, 15 terms in the next one. So 15 nodes will be there correspondingly. So this is how this Pascal triangle helps in writing the displacement model. Similarly, for a quadrilateral element, so quadrilateral element means 4 noded elements. Normally minimum is 4 noded. In that also same thing holds good. So but here what happens when you are taking when you are writing the displacement function, you should be careful in the case of quadrilateral element because x and y should be similar. That is, you have to write it in symmetric manner or cyclic manner. For example, here in the first one, of course, it is u of x y is a1 only. If you take the first row, second row if you take, it will be, now you can see here, it should be symmetrical about both x and y. In the case of second one, there will be 4 nodes here. In the case of quadrilateral, first one is only one node, constant. Then for the second one, minimum 4 nodes will be there. Since you have 4 nodes, you should have 4 generalized coordinates a1, a2, a3, a4. How to write that? So a1 is the first one plus a2x plus a3y. Then we have to take this xy because it is xy is symmetrical. You can see it is symmetrical. Both x and y terms are there. You cannot take x square or you cannot take y square. Only xy term we have to take because both x and y are there. This is how we have to write. For quadrilateral element, you have to be very careful. And you can stop there because there are only 4 nodes. Next comes 9 nodes. For 9 nodes, you should have 9 generalized coordinates, that is a1 to a9. How to write that? Let us see here. So first we have to start from here only. a1 plus a2x plus a3y, you can read out here, plus a4x square plus a5xy plus a6y square. Then you cannot choose all these 4 because there are only 9 elements, only 9 terms here. Only 9 terms means already 1, 2, 3, 4, 5, 6. 6 terms are already over. So 6 terms are over. 1, 2, 3, 4, 5, 6 terms are over. So you are left with only other 3 terms. Out of those 3 terms, which one we have to take? So after this y square, so I have written here x square y xy square, then xy y square. See, these three are taken. The reason behind that is it should be symmetrical about x and y. See, this term is okay. These two terms are okay because in one term x square is there, in another term y square is there, and y and x are there. Next comes this fourth term will be, since it should be symmetrical, we have to consider this x square y square term only. We cannot take this term or this term or this term or this term because both x and y should be there in that. So that is the displacement model for a line-noded quadrilateral element. So like this, by understanding the Pascal's triangle, we can always write the displacement model for a given element.